Yeah, thank you so much, Bennett. Do I have to use this microphone, or is it fine for also Zoom audience and everything? Zoom, okay? Okay. Yeah, it's my privilege to speak also between giants today. I'm a trained computer scientist, studied at KIT in Germany and Imperial College London. And for the longest time, I tried to convince clinicians of the potential of AI, but I think these times are over now. And more recently, I've been thinking a lot about the role of academia, given that, big tech has all the compute, maybe sometimes also all the data. And there's a lot of answers, I guess, to the question. I will share with you two of the aspects that I've been doing in my lab. And actually, not only my lab, like Bennett mentioned, in terms of benchmarking, I've been working with this amazing team here. It's actually a team on behalf of the MICAI Society. You may know that's the biggest medical image computing society, basically worldwide. And we're basically leading the benchmarking efforts there. We have looked into benchmarking from many different angles, from data, from organizing challenges to metrics, rankings, reporting. I'm actually going to talk about this a little bit more detail tomorrow at the Zayat workshop. But I will cherry pick one example, which is metrics. So we've analyzed which metrics are being used in the community. The most frequently one is actually the DICE coefficient, which is closely related to IOU, which in this community, I guess everybody would know. As you know, it basically gives you a number between 0 and 1 when you compare a reference here in blue to a prediction shown in orange. So what happens when we apply such a metric in clinical practice? Well, this is a real life example, analyzing basically the performance of an algorithm that won numerous competitions. And it was, according to current benchmarking, ready to replace a radiologist. So you see the annotation is quite good when you compare it to an expert reference. But now if we scroll through this very slice, you see that there's a small metastasis shown in red that has been missed. And this is actually courtesy to Klaus Maier, Hein, Janet Kirchhoff at DKFZ. They analyzed a lot of data and showed that this is actually a phenomenon that occurred at scale. So at scale, the tiny lesions have been missed by the algorithm. And that's, of course, a clinically very relevant problem. It's actually a disaster to miss disease progression. So how could it have happened? And here we have, one benchmarking problem, but of course also an algorithmic problem. And this is, of course, because sometimes ideally, you would align your losses in your neural networks with the metrics that you use. And in the DICE, what we're actually doing is we count pixels, right? And if you think about it in such a 3D volume, the big tumors, basically has tens of thousands of pixels, and the small lesion only has very few. So in the validation, when counting pixels, basically the small lesion is noise in the validation. So instead, in this specific problem, we should have counted objects instead, right? So we should have phrased the entire problem differently, counting objects via instance segmentation or object detection. Second example, also I think very relevant in medicine. So what I see a lot, and remember that a lot of imaging problems in medicine are actually private. What I see a lot is somebody saying, well, we achieved an accuracy of X, Y, and then somebody else et al. Achieved something else. So this is a really flawed comparison, as you probably know, because accuracy, which is the most widely used classification metric according to our analysis, is prevalence dependent. So depending on class frequency. So if you apply the very same algorithm, you see it here by means of example, the very same algorithm to a different data set with different prevalences, same sensitivity, same specificity, you get an entirely different result. So that's a problem of prevalence-dependent metrics in general. And you can fix it with, for example, balanced accuracy or metric. I'm a fan of this one, EC, which is expected cost. So again, I'm not going to spend too much time on this. Just to mention that we formed the Metrics Reloaded consortium. This is also an initiative of the MICAI special interest group, but also Project Mona and Helmholtz Imaging. It was a big team effort involving thought leaders around the world. I want to specifically acknowledge the core team, Annika Reinke, who's still with me, and Paul Jäger, who's meanwhile with DeepMind. So what did we do? You can, of course, take a look at the paper, but to illustrate it. So first, we spent a lot of time collecting pitfalls regarding segmentation, detection, classification problems, and they concern many different aspects. So the data set, for example, you can see in this specific example, for example, that ECE as a calibration metric is dependent on sample size, but also regarding the properties of the target structures. For example, are the target structures small relative to grid size, or related to annotation and so forth. And then we spend a lot of time abstracting what we found to extract basically the properties of a problem that are relevant to select an appropriate metric. So we abstracted from modalities, we abstracted from domains and said, okay, what is relevant? It's, for example, the fact whether objects are overlapping, whether they're touching, whether we have a high class imbalance and so forth. And then, of course, you can have a look at the paper, what we found, but what you have to do as a researcher is basically to instantiate that fingerprint, report the properties of your problem, and then you're guided through the process of metric selection. So here, for example, you want to get a recommendation for segmentation. So you can instantiate with this tool your problem on the fly. Here you have to decide, okay, do I have a small structure relative to the grid size? Next question would be, am I interested specifically in the center? This has a lot of implications also for metric selections. Do I have tubular structures and so forth? And this basically guides you through the process. Yeah, so there's much more to say actually on metrics, also in multimodal AI times. So if you're interested, yeah, join the SciAD workshop tomorrow. Okay, second topic, research off the beaten track. I don't know if you followed current vision language models, also, of course, from the big tech companies. You see that frequently there's a lot of progress being made. Here, this is the example of Gemini, where the state of the art, which is always shown in red, is beat typically by a beaten, yeah?
So just want to make sure that every virtual participant can see the slides. But you okay?
Probably this whole screen, right? Which is
Not showing.
What?
Let's see what they see now.
Do you see the presenters view or the screen now? At audience? Presenters view?
Yes, we can see. That's what you see.
Yeah. So then I think you have to share the desktop too.
Yeah, let's do the desktop
No.
too. Where did it go? Share desktop too. There we go. Bingo.
Working?
Working?
Okay, sorry to the online audience.
Sorry.
So hopefully now you can follow me a bit better. So what we've seen with the recent developments, that there's been a lot of improvement with these foundation models, but there's one outlier actually, and you see that's a surgical use case, the so-called critical view of safety. So we took a deeper look into this. And we observed that often when you look into surgical data, it's encoded a little bit differently in the larger models. So a question that we asked was, okay, if we look into problems that do not really require domain knowledge, do we see a difference compared to other domains? And well, the short answer is no. So what you see here in the middle is basically, we call it accuracy percentage metric. So let's explain it by means of example. If you take 80%, for example, as a threshold, this means that, so these lines here basically encode the performance. It's the mean performance over many different models over different domains. Then it means that in, for example, 20% of the cases, 80% of the questions were answered correctly for one image. But the main message of this graph really is that you do see a discrepancy to humans. So you see the dashed lines representing human annotators. But really across domains, the questions are answered pretty much the same. This changes when you go towards, basically questions requiring domain knowledge. So the MCC, which you see here as a metric, shows you a 0 is basically random performance. And regardless really of the model that is being used, we don't really solve these domain-specific problems. So there's a lot to do in the surgical domain. So why is this so relevant? It's relevant because, surgery is a high-stakes domain. So if you would treat surgery as a disease, then it would be death within 30 days after surgery would actually be the third leading contributor to death worldwide. So it's really a relevant project. So talking of projects off the beaten track, I want to show you, sorry about this bloody picture. I will not, I think there's a lot, maybe one more approximately. So I want to show you one of the so-called high-risk, high-profit projects, which actually started in 2012. You may know the ERC funding mechanism in Europe, which funds such high-risk, high-profit project with a lot of money. So I want to show you what we've done and also share actually two of our most recent examples. They were just accepted this week in two of the Nature and Science journals. So one is clinically, one is methodological. So 2012, I was a postdoc. I had a limited contract. I was thinking about what I could do with my scientific career. And I was listening to device manufacturers talking about 3D, higher resolution, etc., when interpreting such surgical images. And if you look at it, it's very, very hard to, I think, differentiate anything from anything. And I was thinking, okay, is this really what we need, higher resolution? And it made me think of what Henry Ford had said. If I had asked people what they wanted, they would have said faster horses. And here the faster is basically the ever increasing resolution. So let's talk about the car. So these molecules that you see here are basically main molecules that absorb light in tissue. And you see that depending on the wavelength, also we get a very characteristic pattern for these different molecules, right? So the hypothesis then was that if we could basically take many images of light, not just one RGB image, but many images corresponding to multiple frequencies of light, we could basically recover the molecular tissue composition. So that's called hyperspectral imaging. And you could say, well, but that's what the satellite imaging community has been doing already for a long time. That's true, but they're also not operating in patients, actually. And also, they only take a look at the surface. So let's see how we can go be underneath the surface. This is actually my institute's logo. So if you would basically acquire a 3D ultrasound image, what would you see? You would see the sponge, you would see the sign, but you would not see what's written on the sign, right? Just like you don't see the color of an embryo's eyes or the skin color. So now let's assume we illuminate the tissue with laser. Now my animation is missing. Okay, animation is missing, so I have to explain it to you. So you illuminate the tissue with laser. Again, the photons get absorbed depending on the molecules and the wavelengths. And because of this absorption, heat is produced. It leads to expansion of the tissue, and this in turn leads to an ultrasound signal that you can measure. So now all of a sudden we have a multimodal modality, ultrasound plus optical information, and you can see, for example, the text here. Okay, long story short, for now, all you need to know is that we measure at different frequencies of light, and we can do so both at the surface and tomographically, and we get in each pixel basically a whole spectrum of values. That's all you need to know. And making long story short, because I want to come to the more neural network relevant aspects, we solved all the regulatory issues. We solved the absence of ground truth using synthetic data and so on. And with this, we then eventually found basically a new window into the body. Now you can basically monitor hemodynamics in real time. We can, for example, have a project on developing medication against stroke by monitoring the oxygenation in the brain. We can better differentiate tissue. But I want to show you one very recent example, which is related to sepsis. So you may know some of the sepsis work actually using the analysis of vital signals. So sepsis is very relevant. So in fact, every fifth death approximately is associated with sepsis. And something that was interesting in the context of this new imaging method was that the endothelium is basically damaged, and this leads to microcirculation orders. And we hypothesized that maybe there could be water concentration changes that we could potentially measure. So why did we think so? Because if you look back into this graphics here, then you see that water starts being highly absorbed, basically, when you go into the near infrared. Okay, hypothesis, we can basically take a snapshot with hyperspectral imaging and diagnose sepsis. So we basically acquired images of all critically ill patients in Heidelberg, no matter with what condition they arrived. So this is very unique because it's quite easy to always differentiate healthy volunteers from critically ill patients. But if you have to do a differential diagnosis, this is much more difficult. And long story short, this has just been accepted. We basically found a new biomarker for sepsis. And it was even better when we combined the imaging information with some clinical values, more detailed in the paper. Now, more on the technical interesting part, let's say the neural network part that was interesting recently. So we basically had shown that the new modality gives us a lot of value in proof of concept studies. But as you know, neural networks in the wild are much more tricky. So we've been looking into how can we actually make our methods generalizable. And if you think about it, it's actually a problem that is fundamentally interesting whenever you develop a new imaging modality, right? Because you will never have large scale, internet scale data. You will have to work with whatever you have at the moment. So what can we do? So first of all, I already mentioned, I will not talk into this today, about this today in depth, is prior knowledge. So we've worked a lot with synthetic data, for example, doing test time augmentation. When we knew, for example, we had trained an algorithm with well-perfused tissue, we could do test time augmentation using digital twin data to boost performance. Then we also leveraged other modalities, specifically RGB images, to capture variability in terms of geometric knowledge, right? So for example, we use the diffusion model to synthesize hyperspectral images based on basically mass that we could obtain from another modality. But the one thing I want to talk about today is something that I find quite interesting, which is what if camera techniques evolve? So we cannot basically assume that everything remains constant. And we thought about the question, how can we actually leverage different data pools with different camera characteristics? So in the past, what you would do is basically you would have data silos corresponding to RGB images, to MSI or hyperspectral images, and you would train methods basically dedicated to these modalities. Now, what we wanted to achieve was to have one common framework into which we could inject any camera, basically. So how it works, so the upper part is basically no novelty, that's standard workflows. The novelty lies in the lower part, where basically we wanted to achieve this integration of different modalities. So we were inspired by the spatial encoding or also temporal encoding that you use with other modalities, for example, EHR records. So what we do is we basically encode each wavelength of an image. So this can be any size of an image in these tokens. And then using these learned query representations, we achieve basically mapping whatever input data we get into one fixed length representation. And then with that, which is basically supposed to encode all the spectral information that we need, we can basically do whatever we want as a downstream task later on. As a side note, we also solved the self-supervision aspect of this. Here we were inspired by the JEPA framework, which basically does spatial self-supervision. We expanded it to spectral self-supervision, where we simply do the masking of basically different wavelengths rather than different masks on an image. And yeah, long story short, I will not show you all the details, but what impressed me personally was that this actually worked across domains. So we developed it for medical, but we also tested it on automotive images, on satellite images, and it just worked. And to give you one example, here, this is automotive, obviously, and there's a HSI city data set, which is used for testing, but there's one class that was contained in the test data, but not in the training data. So we also trained on cityscapes, because now we have this framework which integrates data from any modality, basically. And you see that through also leveraging the RGB data that was available, we were able to better classify the pole classes. And then last example, just accepted yesterday. I'm quite excited about this just because I found the idea so interesting. So 5 years ago, I was fascinated about this concept of xenotransplantation, where you take an organ from an animal and you basically transplant it into a human. And I was thinking, okay, this is exactly what we need in a machine learning setting, because often we have preclinical data, we have animal data, because it's, much more easy to obtain, right? It can be obtained under very controlled conditions, and we have to somehow leverage this knowledge and code it in animals for humans. And well, I thought it could be maybe more trivial than it actually was. So we did all the obvious things. And this is just one example. We did co-training and transfer learning, disentanglement and latent space, all these things that you would normally do. And they all didn't really work because the spectra that we got, the data was just too different. And then we thought, okay, but there's definitely shared pathophysiological mechanisms in animals and humans, right? So there must be some way to leverage this. And then we realized that if you look into relative changes, you do actually, so now you have the animals encoded and humans encoded in different colors always. And you see, if you look into relative changes, for example, when you alter perfusion properties, or when you inject a contrast agent, or when you do something where you would suspect similarities between humans and animals, then you see a similar pattern. And this is exactly what we leveraged. So if you're interested, the paper is on arXiv. With this, we actually obtained a performance boost. So we were basically able to transfer knowledge from animals to any other species, basically. And thanks a lot at this point to my clinical collaborators who worked with us long before AI was a hype. And to end this talk, I want to sneak peek you something that could be of interest to many of you, actually, I think. So as basically a member of the special interest group for MiCA challenges, something that bothered me for a long time is that I perceived the benchmarks that we have, the challenges that we organized, to be not always reflecting the most relevant problems. So it seems like a lot of challenges are organized bottom up. For example, in surgical data science, many people work on gallbladder removal, which is a procedure that is not very clinically relevant, right? So it has very low complication rates. So the question was, what can we do to design benchmarks and make data available to really reflect the interesting grand problems? And we have acquired a new project now. It's a multi-million project to develop a benchmark that reflects real clinical relevance. So we will basically work with international societies to find out what, as a medical imaging AI community, we really want to work on. And then we acquired, similar to humanities last exam, 1 million euros of funding to distribute basically to the world to contribute great data to this benchmark reflecting grand challenges of our time. If you're interested to talk more about this, I'm available at the coffee break. And with this, I think, academia is still a great place to do research. There's a lot of value in being not driven by profit. It gives us freedom. It gives us credibility. And I think there's definitely room for us. And with this, thank you for your attention.
That was an amazing talk. I'm super excited for Metal, and I think we really need those benchmarks because the AI is really good at memorizing stuff. I would like to invite the audience to ask questions.
Hey, thanks for the talk. So on the slide where you had the sepsis diagnosis, where you're creating this novel discovery, is there a way to have that be explained in language by the model?
Basically to explain why the model came to the conclusion. Well, that's a very good question. We took a little bit of a different approach. So what we did instead is we tried to take a physics-based approach to convert also the data that we had into something meaningful. In this case, it would be water concentration. And we found, for example, that actually the water concentration goes up. However, now that you say it, it would be interesting, using this more like as a ground truth or what's really happening to see whether a model could actually recover this. That would be super interesting. Yeah. Good question.
Yeah. We have time for one more.
Okay, I'll ask a question. You showed the website where you can put in, details about your problem and it guides you to the best metrics or loss function. Does that work for volumetric images, MRI and CT, or is it for 2D?
No, exactly. So we made sure this was a core, let's say, methods challenge that we had to abstract from the specific modality that we have. So it can basically take any, so far it's static images, but we're working on a video extension at the moment, which gives us, some more problems, but we will actually release something rather soon on the video as well. Yeah.
Thank you so much, then.
Should I stop sharing or you do?